We're going to begin this lecture with a discussion of Theorem 3.1.12. Before we discuss the theorem, let's recall what the minimum degree of a graph is. The minimum degree, which is denoted by small delta of g, is simply the minimum of the set that lists all the degrees in the graph. So the theorem states that if T is any tree on n vertices, and G is a simple graph such that it has minimum degree at least n minus 1, where n again is the number of vertices of a tree, then we know that the tree T is a subgraph of G. So for example, let the graph G be a cycle. So it has min degree equal to 2. And therefore it's easy to see that this cycle could not contain a tree whose min degree is greater than 2. So what the minimum degree qualifier does, it guarantees that the graph is dense enough. That means that there are enough edges so that any given tree on n vertices can be contained as a subgraph. So for another example, let's just say n is equal to 4. There are 2 trees that we can draw with 4 vertices. There's the path, and then there's the star. The star, or the complete bipartite with 1 vertex in one of the partite sets and 3 in the other. So you have a vertex of degree 3, or you have a path. So what the theorem says is that if the graph has minimum degree at least n minus 1, which would be 3 in this case, if it has minimum degree 3, then it must contain the 2 trees, the path and the star, as a subgraph. So here is a summary of the properties of a tree. Some of these we discussed in the first section. Now let's list them all. If T is a tree, what do we know? It contains no cycles. Given any 2 vertices, there's a unique path between them. Every edge is a cut edge. It has exactly n minus 1 edges. It has at least 2 vertices of degree 1. And if you add any edge, you generate a cycle. Recall in the first video, we said if you take out any edge, you disconnect the graph, and if you put in any edge, you generate a cycle. So these 7 properties of a tree on n vertices are well known about trees. And you can assume, once you know that you have a tree, you can assume you have all of these properties. So let's look at one of the exercises in the section in our textbook. It says to draw the graph or to explain why no such graph exists. And problem 6 gives the following. The graph has 8 vertices, 2 components. It's a simple graph with exactly 10 edges and 3 cycles. So since we know it's 2 component, we could draw the 2 circles representing each component. We don't know how many vertices are in each, so we could label them with a S and a T representing how many vertices are in each. And we do know that S plus T equal 8 because we're told it's an 8 vertex graph. Now, it has to have 3 cycles. And since these are different components, the cycles have to be contained inside the components. So either there are no cycles in one and 3 in the other, or there's 1 cycle in one and 2 in the other. So let's assume, for our first case, that the component containing S vertices has no cycles. And then that means the 3 cycles are in the other component. But that gives us some more information. If there are no cycles in our connected component, then what do we know about the component with S vertices? It's a tree. Therefore, we know how many edges it has. It has S minus 1 edges. So that tells us how many edges are in the other component, because we're told that we should have exactly 10 edges. So we would have 10 minus S minus 1 edges in the other component. If we try an example and let S be equal to 3, then that means T is 5. Furthermore, there are just 2 edges in the component with S vertices, or 3 vertices. So there are 8 edges in the other component. 8 edges and 5 vertices. So if I try this as an example, where I've got S equal 3 and T equal 5, no cycles in S component, then I would have to have 8 edges in the other. And I want to know if I have drawn the graph required by the author. He said an 8 vertex, 2 component, simple graph with exactly 10 edges. So far, so good. But what about the cycles? It actually said exactly 10 edges and 3 cycles. Does that mean exactly 10 edges and 3 cycles have to be in there? Or does it mean exactly 10 edges and exactly 3 cycles? Does the exactly go to both the number of edges and the number of cycles? If the author intended exactly 10 edges and exactly 3 cycles, then we haven't drawn the graph, because we certainly have more than 3 cycles, and that would change the problem. So what do you think? Do you think when the author said exactly 10 edges and 3 cycles, the exactly was supposed to go to both the number of edges and the number of cycles, or just the number of edges, and then you could have 3 or more cycles? We'll continue the discussion using the discussion forum on D2L, and this concludes video 2.